Right, hello. Welcome to lecture number 7 of the database practice. Database programming in practice. Right. This lecture, perhaps the most important lectures. Why? First, this lecture you really need to use the knowledge of this lecture to do tomorrow lab. Second, you really need to use knowledge of this lecture to do your project. Third, I think 30% of the score in the final exam rely on this. So that's how important this lecture is. Okay? Again, first, your tomorrow lab, actually next week as well, you need to use knowledge from this lecture. Second, the project, you need to use the knowledge of this lecture. Oh, I just think about the fourth one. The third one is actually SP3, rely on this lecture. Fourth, 30% of your final exam depends on these lectures. That is why you really need to focus. If you don't understand, ask me immediately, okay? Okay. Right? Any question before we move in on? I don't think no. I think no. This week's solution project to check out tomorrow. Solo project 3 will be released. But the good news, this perhaps be the easiest solo project 3. This is the only project that you do not need to code. You don't need to write code. No Python, but some SQL. But no Python, okay? If you hate Python, if you like, I don't want to write Python, this perhaps is the easiest one, okay? The checkout perhaps, I'm not sure, maybe easy as well. So before we get through this, let's talk about big picture in technical. So let's say if before I taught you last semester the programming, I want some system, right, that allows you, students, to submit an assignment and auto-grade, show the grade to the users. That is what I want. How can I transform what I want here, requirement here, to the database? So that database management system can keep information that is sufficient, correct, and be able for the system to do all of this. That is the first thing, right? Whenever you get a solution, you need to have some requirements first. I have this requirement. But this is like, okay, this may be a little bit too vague, so I grade it down to something that I call functional requirements. Functional requirements, what the hell are this? Functional requirements is the requirement of the system, typically for systems, telling that what this system can do. What this system must do, must be able to do. Okay? So, whenever you have solutions, blah, 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 requirements, blah, 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 at least you need to break down to a list of functional requirements. List of functional requirements like this. Okay? Am I recorded? Yes, okay. Whenever you get requirements, please make this list. Okay? List of functional requirements. Each bullet point must tell what this system must be able to do. I always use the word must be. You see, must be, because it is a requirement. It's not a good to have list. It is not should have list. It is requirement. It is required. It is mandatory. That is why all the requirements, you must say users blah blah must be blah 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 blah. This must be blah blah blah. You cannot use user should be able to submit. No, that is not a requirement. That is a good to have list. Okay? This is important. This is really important. Okay? Requirement must be, must. You need to use the word must, and must. Okay? That's good. Yo. Okay. Again, whenever you want to do something, some system, make a system, you need to at least have a list of functional requirements. Functional requirement mean what must this system be able to do? Again, must, not should, must. For example, users must be able to submit an assignment. Submissions must be able to be auto-graded. Users must be able to see the grade of the submissions. Okay? Then, given these functional requirements, this functional requirement means that if I can make all of these requirements happen, you can do this, right? You now make a system that allows users to submit an assignment, grade it, and show the grade to the users, right? My question is, given these requirements, which kind of information should we keep? Can someone tell me? Let's say if I want the system to have this function like users must be able to submit an assignment. Users must be able to submit an assignment. What kind of information should we keep? System doesn't need to be software, you know. Let's say user must be able to submit an assignment. So which kind of information do we need to keep? At least you need to know that users submit an assignment, right? The assignments and users. Which kind of information should we know? Do you need to know the information of the users who submit the assignment? You should. Should you know the assignment, the information of the assignment that users submit? You should. Should you know the information of which user submit which assignment to which assignment? You should, right? At least you need to do something like this, like users assignment and maybe the submissions, right? User, maybe Audi submit solo project 1 with Audi.zip, right? At least you need to know this kind of information, right? Audi solo project 1, Audi try again, Indie solo project 1, Indie first try, Indie solo project 2, Indie SP2.zip, Poom solo project 2, Poom Z.zip, something like this. You need to think about this. You have this table. Now your system will be able to know, oh yeah, this user submit this assignment using these submissions, right? So your database can tell this information, right? Can tell that users submitted assignment, which user submit which assignment, right? With which submission. Okay, I can just use this table, right? So now I have this table, so I can now sort data sufficient for making a system do this, right? The problem. First, my question is, how do I know whether this Audi and this Audi are the same person? My name could be Audi as well. Your name could be Audi as well. You can be Audi as well. So, Are these two the same? I may be Audi, you may be Audi, you may be Audi, you may be Audi. Everyone is Audi. Audi, first Audi submit solo project 1. Second Audi submit solo project 2. 1. These two Audis may be the same Audi. Or these two Audi may be different. How do we know? Like these two indie may be the same indie. Or these two indie may be indie and another indie is, I don't know. This is what I call the ambiguous information problems. And this problem occurs if your design of your database schema is not good. The second problem is data redundancies. I mean, we talked about this before, right? Let's say, okay, given this information, all these solo project 1, all these solo project 1, right? Let's say, hey, now I don't want to use the word solo project. I want to use the word I want to use maybe the word solo assignment instead. So, okay. I don't want to use the word solo project anymore. I want to use solo assignment. Okay, I fix. So I need to fix it 3 times, right? I need to rewrite this table 3 times. Takes time. Also, this is a small table. Imagine that you have 1 M submission. How can you be sure that all this solo project will be changed? If you have a lot of data being redundant, then it takes time. And if you manually edit it, then it could be an error as well, right? It's the margin of error is larger. Right. Also, I'm not talking about the old problem, the ambiguous information, right? That these 2 solo projects may be from different causes as well, right? Okay, this is just an example. So that is what I want to say. What I want to say is that, what I want to highlight is that, okay, that's fine. You can create your own table to store your own data. But if your design of the database schema is not good, you're going to have this kind of problem, which I don't think you want it. The question is how? How you will be able to, how you can design a good database schema. Today, I will present to you the standard approach that many people use to design database schema. When we talk about designing database schema, alternatively we can say that it is the phase that we call a logical database design, right? This is a standard approach. Not many people would say that. I will tell you the approaches, right? How many approaches are there? The second one is, even though we do the standard approach will give you some clues, some pieces of information. That is not a relational database schema. You will need to use the method called reductions to reduce from the information you get into the relational database schemas, right? So let's talk about some approaches first. Nowadays, when people design database schema, relational database schema, there are multiple ways. The first approach is you get the business requirements, you get the functional requirements, you use it and form something that's called an entity relationship data model. That is a first approach. first approach. And that is our focus today. The second approach is that you use the design theory that Ted Cott is the one who invented the relational data models. Put it in the paper back in 1970s or 80s. They call it normalization theories. You can use it. It helps you solve data redundancy problems, definitely. But for the first problem, no, it doesn't help. So I would say that it is not that popular because it's based on mathematics that is kind of rigorous, right? Next lecture, next week, we will talk about this, so you will see how hard it is, and it will be in the exam as well. Okay. The third way, use common sense. If you are experienced enough, you design tons of database schema, you will have some sense, common. You will see commodities, and you don't need to use the first approach. You just need to, okay, based on this requirement, you need to have this table, this table, this table. Okay. The third method, I'm saying that this is the most popular method people use nowadays. The problem with this method is that it's not scientific. Another problem is that you need to have enough experience first. That is why I'm not going to teach you this, because I don't know how to teach you after. You need to have enough experience. These two, the good news is that these two approaches, they are scientific. They are solid. So they are systematic. So if you learn it, you can follow it step by step, in order to get a good relational database schema. Okay? So if we're gonna go to the approach number one, and in the approach number one, we need to know this first, another data model rather than hierarchical, network, relational, blah, 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 which is the entity relationship models. And I would say that this model is not that hard to understand. Perhaps this is more intuitive than the relational data model. What? Okay, so again, every time you learn data model, it's always about theory, definitions, terminologies. You at least need to know two things, as the name suggests, right? Entity relationship model. So you at least need to know these two words. Entity set and relationship set, okay? First, entities. Entity is a unique thing. An entity is an object that exists and is distinguishable from other objects. Exists and distinguishable. For example, I am an entity because Guy is exit, right? Guy exists, right? And I can be distinguishable from all of you, right? You is also an entity. You is also an entity as well. You at the back is also an entity as well. You are also an entity as well. Because we exist and we are distinguishable, right? This is entity. Specific person, specific company, specific event, specific plant. See, always specific. Specific group of people is also an entity. This classroom is also an entity. All of us together can also be an entity. It must be something that exists and is distinguishable. This light is also an entity, right? So this is the, So, do you know what is entity? Okay? Yeah. The next term, which is the most important term, entity set. As the name suggests, basically a set of entities. That's it. But. Not just that. Okay, true, it's a set of entities, but it must be a set of entities of the same type. For example, I have a set of guy, which is me, and maybe class, room. What is this 102? Is it an entity set? Not quite, right? Actually, based on the definition, but guide and classroom, they're not the same type, right? But if you use this guide, indeed, is it an entity set? Actually, it depends on the definitions, but likely it is, right? They are all people, they are all persons, especially they are all staff of this course, right? This is what we call an entity set. And this will be an important definition that we will use in the entity relationship data models. Okay? Any questions, comments, concerns before we move on? When you represent an entity set, you are representing it as a tuple of attributes. Actually, a set of attributes, tuples, regardless of what. For example, I'm saying that in structure, I have an entity set of instructors. For each instructors, I can describe each instructor using the ID, the name, maybe salary, like this. So these are what we call attributes of the entity set. Which means in this entity set called instructors, all entities in this set must be able to describe with ID, name, and salary. Any questions? Then, this will be another term before we get to the relationship. Subsets of attributes in the entity set form something that we call primary key. What is primary key? Primary key is a subset of attributes that can, this is important, uniquely identify each member of the set. A subset of attributes that can uniquely identify each member of the set. For example, I have a set of instructor. I have this set of instructors. Let me ask you, which attribute or which subset of attributes can be primary key? Can uniquely identify each member of the set? Which one? Which one? Can ID uniquely identify each member of the set? Yes? Can name uniquely identify each member of the set? Yes? Alright. In this case, yes, but in reality, if you think about it, people may have the same name. So you should, right? Is salary can uniquely identify each member of the set? which means the good primary key would be ID. Name can be also an primary key as well. Or you may use maybe ID and name together as well. That's fine as well. Primary key doesn't need to be a single attribute. It can be a subset of attributes as well. Okay, like a student. Let's say if you don't have an ID, you may use first name and last name to uniquely identify each student. But I mean, it doesn't always true, right? You may have someone who have the same first name and last name as well. That's why typically just put ID on each entity set. Make it uniquely identify things. Okay. Okay, so now you know entity set, right? Entity set can be represented as a set of attributes, right? You may have entities in the set. Once you have an entity set, in entity relationship data model, we represent the schema as a picture, as a diagram, like this. Let's say we have an entity set called users. This entity set has 3 attributes: ID, name, and type. ID is a primary key. When you have this information, you first draw the entity set along the name. Then you print the attribute as a circle. Pointing out from the entity set. For primary key, you underline it. For attributes, that is primary key. That are primary key, underline it. Okay? This is how you represent the schema in entity relationship models. Okay. Actually, this is one of the notations. We call it Chen. Right? Indeed, Chen model. Chen. Yeah, Chen model. Yeah. Well, maybe I have another entity set called assignment. I have ID and title. I have another entity called submissions. I have ID and file name. Right? So, what I want to say is that if you want to decide using this method, first, given functional requirements, you need to be able to identify entity sets. Okay? Entity sets is a piece of, it should be something that you are interested in, your system is interested in. For example, user must be able to submit an assignment. Users, assignments, submissions. These 3 should be entity sets of in this diagram, in this entity relationship model. Okay? Then that is the entities set. Next one is your relationship set. Before we get into the relationship set, you need to understand relationship first. A relationship is an association among several entities. For example, K-DAI is an entity, right? DBPs also can be an entity as well. DBP exists, right? Even though it's not tangible, but it exists, right? Guide, DBP. What is the relationship between guide and DBP? Guide, maybe, is an instructor, right? Of the called DBP, right? This is relationships. It doesn't need to be among two entities. It could be among multiple entities as well. 3, 4, 5 as well. This is a relationships, right? For example, Audi with Audi, but now I don't identify Audi using the name. I identify Audi using their ID because I know that ID is unique. 234 submits 99911. This form a relationship between Audi and Audi.zip, right? We write the relationship using this as a pair. Actually, it should be a tuple if you have more than one entities, right? But yeah, if you have only two entities, then use a pair, right? And this relationship has a type of submit. Submit is the relationship type. Okay? Next, relationship set. Holy God. It may sound weird, but basically, relationship sets is back. It's actually a mathematical relations. Have you learned relations before? I think you have learned it before, but never mind. It basically relations among more than or equal to entities each taken from each entity sets, or this mathematics formulations. So what does this mathematical formulation mean? Mathematical formulation means that, okay, you will have a set of relationships where the first entity comes from the first entity set. The second entity comes from the second entity set. The nth entities come from the nth entity set. That is it. This is a relationship set. For example, I have a relationship set called submits. In this set, and submit here, E1 must be a student who submit it. E2 must be submission. Then means that the first element of a pair must be student, for example, Audi. And the next one must be the submissions. Let's say I have the file Audi.zip. So this is the relationship set. Okay? Understood? Any questions, comment, concerns? Well, this may look a little bit cryptic. Let's be more pictorial. So, each entity set is basically this part, right? This is an entity set. This means that we have two entity sets, right? An entity set of users and submissions. An entity set of users and an entity set of submissions, right? Each can be uniquely identified by the IDs, right? A relationship set means a set of relationships between two entity types. For example, Audi submits Audi.zip, Audi.try again, or zip, which are 99911 and 99912, right? Indy submit 99921, 99931. Poom submits 9956. These relationships are in the set called submits, and this is the relationship set. Any questions, comment, concern? So now we form relationships between two entity sets, right? In terms of diagrams. When you represent it in the ER data model, entity relationships can be called ER, okay? ER is an emergency. ER data model. Relationship sets can be represented as this diamond shape. Let me put submit inside it. So when you read this ER diagram, it will be like users submits submissions. Okay? But not done yet. If you write this and submit to me, zeros. Okay, it's not yet done. Okay. Moreover, each relationship could have their own attributes as well, could have an information as well. For example, hey, this submit can have the time of submission as well. That is fine. That is fine as well. We do not only record who submit what, but now we record the time of the action as well. So, if that is the case, then what we do is we will try to put attributes on next to the relationships set. Okay? So now we have users submit submissions on this timestamp. Okay? On this date and time. Okay? Okay. Not done yet. Okay? Right? But and as I told you, relationship doesn't need to be among these two entities. It could be from these three entities together. Like this user submit this assignment as this submissions on this timestamp. If you have this, if you are in this situation, we call it a ternary relationship, which is pretty rare. Right? Normally, okay, I would say it in this way. Normally, we usually have binary relationships or relationship among two entities. It's very rare. The reason why it is very rare is that, first, it is hard to use this as a relational database schema. The second one is that you can always break down this into binary relationships. Okay. Not yet done. Okay, not done yet. So, for the attributes, I only tell you primary key, right, and normal attributes. Actually, there are more type of attributes that you can draw in obvious diagrams, like composite attributes, multi-value attributes, derived attributes. I'm not gonna cover them. Okay, this is for me out of scope. I mean, if you want to know more, then you can read more on the internet or ask me. But again, this is not yet done, right? Because I haven't introduced the most important things, which is what we call cardinality constraints. Cardinality constraints express the number of entities to which another entities can be associated via a relationship set. Oh my God, what the hell is this? Means that for each two entity sets, what are the types of the relationships? They are basically 4 types. There could be more than this, but this is 4 important types. The first type is one-to-one. One-to-one means that, let's say A is student, B is submission. One-to-one means that, one-to-one means that one student can only submit at most one submission. And one submission can be at most from one student. Okay? Okay? You cannot have one student submit multiple submissions. And one submission belong to more than one student. In this case. Next is one-to-many. One-to-many means one student may submit or may have multiple submissions, or may not have any, or may have one. 1, 0, many. That's fine. But one submissions only belong to at most one student. Okay? The third one, many to one. Similarly, one student can only, or one or more students or 0 students can submit, can have only one submission. One submission may belong to multiple students. So each one can submit at most one submission, right? So this is many to one. Many to many means one student may have multiple submissions. One submission may belong to multiple students. Okay? Do you understand? Understood? Understood? If you understood, then tell me, realistically, student and submission, which should be the most appropriate relationship type? Realistically, between student and submissions. Choose one student submit only one submission, and one submission only belong to one student. Really? Let's say, okay, in big grade, let's say more realistically. Can students submit more than one submissions? Right? So definitely it's not one-to-one. Also, it's not many to one. Because many to one means that one student can only submit one submission. So it's either one to many or many to many, right? Then you need to ask yourself, can one submission belong to multiple students in big grade? Not sure whether you have used these functionalities or not, but in PP last semester, can one submission belong to multiple students? Yes. Right? So between student submissions, the correct cardinality constraint is many to many. Okay? Clear? This is the most important part of this lectures. You need to be able to identify entity sets and relationships among them. More importantly, identify cardinality constraints between them. Okay? So, if you now get the cardinality constraints of the relationships, when you write down, you write this: one user can submit multiple submissions. One user can submit. So when I do this, I do it this way. One user can submit one submissions. One submissions can submit can belong to one user. And for each one, I pick the highest one. So eventually, I will have only one and one. Okay. So in the realistic way, it will be this one, right? Many to many, right? Means that one user can submit multiple solutions. One submission can belong to multiple users. And we pick the highest one, which is n. The highest one, which is n. So, which means eventually you only need to write m and n. Someone may say that writing m and n look hard, so in some case you may write m as well. M and n. That is fine as well. Someone write it this way. But I don't mind. Okay? If you send me ER diagram, whether in the project or whether in the SP3 or whether in the exam, without this cardinality, you're not going to get scores. Okay? Any questions? We have 10 minutes left, and we're going to get through the fun part, I hope. So, okay. Now we have fancy entity relationship models, right? We have some fancy diagrams. The question is, this diagram is a table. How can we create a table from this diagram? No, right? So how? Then you need to do reductions. You need to reduce this to relation schemas. So The first step is that you analyze your requirements, you identify entity sets, then you identify relationships among them, you draw the diagrams here, and then you reduce it to the relation schemas. In order to reduce it, I think the title is wrong. Don't mind the title. Follow these steps. First, which entities? Each entity can be mapped as a table whose columns are the attributes of the entity set. Pretty straightforward, right? We have this user. So basically, in the database, you should have table for users, right? We have the submissions. It means that in your database, you should have a table for submissions, in which users will have 3 columns, right? ID, name, and type. Submission we have 2 columns, ID and findings, right? Right? That is the entity set. How about relationships? Which is important as well, right? Relationships, you need to resolve it. It depends. How you resolve it depends on cardinality constraints. That is why I'm saying that the cardinality constraint is the most important thing. If you see 1 to 1, you need to add foreign key column. The first foreign key back is back, right? You need to add 1 foreign key column to either of the tables, referencing another table's primary key. So, any table, either left or right, just need to have 1 more column. And that column must be a foreign key referencing to the primary key of another table. 1 to 1 is easy. It can be confusing. The fun thing is 1 to many or many to 1. You add 1 foreign key column to the table with many sides, referencing the 1 table primary key. Then, if your relationship set has attributes, it goes as columns along with the foreign key. Okay, I will show you an example. There it is. And this too is okay. You just need to add columns, right? If 1 to 1, you add only 1 foreign key column along with the attributes. If 1 to many, you add 1 foreign key column, right? Along with the attributes if it is. But if you have many to many, you need to create another table. If you have many to many, you need to create another table. In this table, primary key of this new table must be a composite key, or basically primary key that has multiple columns. Right? This another table. Primary key must be both table primary key together. Okay, so you bring primary key from the left hand side and the right hand side and create new tables where both of them are the primary key of the new table. And both of them must also be foreign keys as well. Let's see an example. So let's say we have this one. This relationship is 1 to 1. What we need to do is, okay, we have user table, we have submissions table, that's fine, right? That is the first step, which is pretty straightforward, right? Then, 1 to 1 say that we need to add a foreign key column on one side, on either side. So let's say if I add on user side. So I can just add this column to the users. This column must be foreign key referencing the ID of the submissions table, okay? Which means all values here must be primary key from the submissions table, right? If you do this, then you have enough information, right? You know that all submit these submissions, right? Indeed, submit these submissions. Boom, submit these submissions, right? And how are you going to know whether which submission belongs to which users? Join it back. You join. That is why we have join. You see it, right? 99911 match with this, which is Audi, right? 99921 match with this, right? 99956 match with this, right? But this is one-to-one. This is assuming that we assume that user has one submission. One submission has only one user. So you see that one user, Audi, has only one submission. Indie has only one submission. Poop has only one submission. Each submission can have at most one user, right? This one from Audi, this one from no one, right? This one from Indie, this one from Poop, this one from no one. Okay? How about one too many? So this is one to one. One too many. One too many. So now I change this to many. If it is one too many, the rule say that you need to add one more column on the many side. This is the many side. You add one more column here where this is the foreign key referencing users. So when you interpret it, now you know this 9911 file name is ordinal zip belong to user 234, right? Which is this, right? 9912 belong to user 234. 9921 belong to 345, right? 345 and 567. And you see, this states clearly that one user can have multiple submissions, right? But one submission can only belong to one user. And all the timestamp here that you put here, you must need to put it right here. So you know that, hey, this is the timestamp of the action submits. Okay? Actually, on the previous slide, timestamp, you should have timestamp here as well. On the table that you put foreign key on, okay? All right, any questions? This is really important, right? So, the question is, how can you, let's say you want to get the name of who submit audit.zip. Audit.zip is on this table. Name is on this table, right? This is where inner joins comes, right? You do inner joins, right? Now you should use join to reconstruct the information back together, right? That's it. You use join. You join this column with this column, right? Join them back to regain the reconstructed information back. That is why join is very important. The last one, many to many. I told you, many to many. What we need to do? What we need to do is we create another table here where this table we have at least two columns. These two columns, the first and the second one must be foreign key to the left and the right table. And also, both columns must be the primary key of this table. Okay? So, if you look at this carefully, it means that if I draw the line, you're going to see that it will look like this, right? Right? If, let's say, if maybe audit.zip it may be submitted by both Audi and Indie. I can also put this as well. Another rule, which 3, 4, 5, right? Indie and submit audit.zip as well. So if you create another tables here, it allows you to put in information of, hey, both Audi and Indie, submit submission 99911, submit the same submissions, which makes many users can submit one submissions happen, right? So that's why we need to create a table. How about the timestamp here? Where should timestamp belong to? The same rule, timestamp must go with the foreign key column, which is, in this table, you must also put the timestamp column as well. Okay? To reconstruct the information back, you need to join these three tables together. Right? You join these three tables together. Join user ID with this user. And you join submissions and this ID together. So you do 2 hop joins. Right? And that's it. So, in order to design a good database schema that doesn't have much problems, first, you always need to know the requirements. And you should break down the requirements into a list of functional requirements. Okay? Next, one of the good ways to start is to draw ER diagrams from the requirements, from the list of functional requirements. Tomorrow, you will get to do it in action. And you see like, okay, this is what should you do, this is what you shouldn't do, right? Then apply normalization theories if there is an opportunity to do it, in which we will cover it in the next lectures. This will help you ensure low data redundancies, okay? Any questions, comments, concerns? If not, that is all for this lecture, for the lecture today. Even though this lecture may be a little bit short, but tomorrow lab, SP3, your project, your final exam, rely on these lectures, okay? Try understanding this. Okay, any questions, comments, concerns? If no, then we may go and eat lunch. Hey.